We now move to the final topic, perception, and this is chapter 3 in the textbook. So we start off with the question of what perception is for, and as we point out, there are at least two basic underlying functions of perception. One is recognition. So this we can think of as offline perception, where you're not doing something specific, but you're just recognizing what objects are in the world, versus action, visually guided or perceptually guided action, such as avoiding obstacles or picking up an object. And both of these we need perception in order to do both of these kinds of things. We start off with the observation that sensation and perception, although related, are two different things. So sensation is what your sensory system does. We talked about sensory receptors. So there are sensory receptors underlying the five senses: touch, smell, seeing, and hearing, and taste. And what these sensory receptors do is take measurements of the environment. So it may be measuring chemicals in the air in the case of smell or taste. It may be measuring pressure or heat in the case of touch. Maybe measuring light in the case of vision, or maybe measuring the vibrations in the air in the case of hearing. But this is not perception. As I said, perception takes place in the brain based on these stimulations, these measurements. Our brain has to make inferences, guesses about what is causing those specific measurements, what's going on out there in the world, which is what we ultimately want to represent. Some examples, for instance, we may have pressure and heat on your hand, and based on that you may interpret that as someone else is touching your hand. So the basic measurements are of pressure and heat, and the interpretation is of another person touching it. We can see that perception very often depends on guessing, that it's indirect, that there's a gap between the sensation and the perception. So for example, we see a circle behind a square in this case, but of course that's not the only possible interpretation of what this is, but there's a certain sense in which our brain will tend to generally make certain guesses over and over again. In this case, we say the stimulus, sensory stimulus, is ambiguous. It's ambiguous whether what's actually in this scene here. In this case, the ambiguity, as we saw in many illusions, is one of depth, is where's the circle and where's the square, which one's closer or further away in depth. And the perceptual system makes a best guess. And as we said, in this case, the reason it's a best guess is because there are lots more circles than there are these kinds of Pac-Man shaped wedge objects in the world, so there's more likely to be a circle. And also, the edge of the Pac-Man, if that's what it was, so something like this, and the square would have to be perfectly aligned. It seems much more likely, in some sense, that there just happened to be a square somewhere in front of a circle. So this is actually a reasonable guess, and this, in general, what we're going to find is that the perceptual system is making what we consider a best guess based on the considerations that it has at hand. So a particular example of the ambiguity, of the inherent ambiguity of a stimulus, is lightness. Trying to figure out whether if something's black or light or white or gray. When we see it that way, what that is, whiteness or grayness or blackness, has to do with how reflective an object is. So if something's black, it reflects much less light than something that's white. And the question is, how does our brain figure this out? When you see an object or something or a patch such as this one, how does your brain know that this is gray? So the naive answer would be just measure how much light. If there's a lot of light bouncing off of it, maybe it's white. If there's not a lot of light, maybe it's black. The problem with this is that there's inherent ambiguity because you don't know how much light is in the environment. And as we pointed out, a white object under poor lighting is going to reflect a lot less light than a black object will under good lighting, say natural light. So just measuring how much light is bouncing off of it isn't going to tell you whether the thing is actually white or black. It's not actually going to tell you how reflective it is. Now, we didn't actually discuss in any detail how your brain does actually solve this, but the point is that your brain does ultimately make a guess. And we can see that it's guessing from these illusions. So in this case, A and B are really the same reflectance. They're actually reflecting the same amount of light, and that's coming into your eye, but you see them as different for various reasons. Your brain interprets them as different. You can see they're the same when you connect them. And your brain is basically making an inference and saying, well, yeah, this is reflecting the same. It's right now it's producing the same amount of light as this, but this one must be more reflective because this one's in shadow, and if it's producing the same amount of light, then it must actually be a lighter kind of surface. And so what your brain does is make an inference here, it makes a guess that this actually has a lighter reflectance than this one does. And in this case, it happens to be wrong. So illusions are these cases where your brain gets things wrong based on the kind of inferential processes, the kind of guessing mechanisms it has that usually work. And so the brain usually gets perception right. But in the case of illusions, they're carefully crafted to show the underlying assumptions that your brain is making. So we start with the basic structure of the eye. And what I want you to know about the eye is just that light has to enter through the pupil and then reach way back into the back of the eye into this thing called the retina. Light enters the pupil, is focused by the lens, and this lens is something that just changes how the light ends up in the back of the retina. And the retina is made up of these photoreceptors. So these are kind of sensory receptors, which means they do transduction. They change light into a neural signal. There are two kinds of photoreceptors, rods and cones. Rods are highly sensitive, which means that they need less light in order to be activated. And they have lower spatial resolution and do not have achromatic, which means they don't respond differently to different wavelengths of light, so they can't tell the difference between different colors. Low spatial resolution means that they are basically kind of blurry, that they can't do fine level detail. Cones have lower sensitivity, need more light, a higher resolution, they can make finer detailed precise measurements, and they're chromatic, they can measure the differences in wavelength, and so that corresponds to differences in color. In general, rods are more active in low lighting conditions, such as nighttime, and cones are more active in better lighting conditions, such as the daytime. So what does the retina tell the brain? Well, it's got all these rods and cones. It's got about 100 million per eye. And what they ultimately deliver to the brain is a matrix of numbers, measurements of how much light of what wavelength is hitting the eye in different locations in the back of the eye. So you start off with that, but of course what you really want is something like this. When you see a room, you want to be able to see where the objects are, where does one object begin and the other end, segmentation and grouping, where are they in depth, and we recognize what the objects are. And as you can see, it's a long, hard task to get from one to the other. To start off with just a two-dimensional description of a bunch of measurements of how much light and what color that light is, to being able to figure out these more difficult kinds of features of an environment that you really want to know. So how do we do it? There's two basic types of processing that we can discuss: bottom-up processing and top-down. Bottom-up processing is based on the stimulus itself. So regardless of what kind of stimulus it is, there's certain kind of processes you can do based on the information in the stimulus. Top-down processing, on the other hand, depends on the existing knowledge of the particular type of stimulus you are looking at. So you may know something about it based on the stimulus type, that's not necessarily there just based on the bottom-up information, the data in the image itself. So we talked about some examples of this for segmentation. So let's say you see a grid such as this one. You can do bottom-up segmentation. You may not know anything about this, but you may be able to segregate these on the basis of common regions. So if there's similar texture in one place and then that texture changes, you may segregate those up and carve those up into different squares. This we call bottom-up segmentation. You don't have to know anything about it in order to do this kind of segmentation. Another kind of bottom-up segmentation is edge detection, looking for places where luminance changes. This is very important. It's something that we see already in the retina taking place. So places where light suddenly changes from light to dark or dark to light is often going to indicate that there's actually a change in the reflectance, and so that means maybe the object has changed. So it's a white object on a black background. So those luminance edges, as you can see over here, are very important in potentially signaling that there is a change in the object that you're seeing. So edge detection is a form of bottom-up segmentation as well. As you can see, it's certainly not perfect. There's portions of the image where there are edges that you don't see, and then there's lots of edges that aren't really edges, aren't really object edges in any case, object boundaries that you do see. So you need to also employ other kinds of strategies, for instance, top-down information. The Dalmatian, which you, if you were in class, you hopefully recognize here, is an example of top-down segmentation. Once you know what a Dalmatian looks like, you may be able to segment out edges that aren't really there based on the bottom-up information. This is because you're bringing top-down knowledge. It's not based on some generic process you can run or based on the data and the information in the image, but rather you're bringing knowledge to the scene that's allowing you to do that. We also talked about sine wave speech, which was another example of where top-down information can change the way you perceive sensory stimulus. In this case, the auditory stimulus sounded very different when you knew what it was going to be because you already heard the real original version of it, and made the sine wave speech sound very different. And it's another example of top-down information. Once you've got your edges, you also need to figure out, there's something else you need to figure out. You don't want them to know where the boundaries are, where the light-dark boundaries are, but you now need to figure out the depth ordering of those edges and which portion of the image the edge is a boundary of. So you could see this either as black objects, black faces on a white background, or a white object on a black background. So this is a next step after segmentation that your brain needs to solve, and we can see it's again based on the ambiguity of depth. So if it's black faces, then the black is in front of the white, and if it's a white vase, then the white is in front of the black. So how do we go about solving these? In most cases, how do we actually do this kind of figuring out segmentation? So we talked about a couple of cues: symmetry, convexity, parallelism. Let's just talk about the symmetry one. So there's a tendency here to see the black as figure on a white background and not white as figure on a black background, although it's possible to see that. And we said that that bias arises from the fact that in general, there tends to be a pretty high proportion of objects that have this kind of symmetry, so that's present if we see the black objects. And so, when faced with the possibility of black symmetrical objects and white asymmetrical objects, we tend to see black symmetrical objects. So we do the figure ground segmentation based on this property of objects. And as we said, it's not just that there tends to be objects that are objects often tend to be symmetrical, but it's also that it's very unlikely to have symmetry between objects. So let's say it's white as figure. Well, we would have to be a very special kind of arrangement of white objects that would lead to this kind of symmetry between their boundaries. And that the brain seems to think is just too strong a coincidence. It seems much more likely that there are in fact black objects that have symmetry rather than white objects that are asymmetrical that happen to be perfectly aligned to produce this kind of symmetry. So the point is that the brain is doing something, making an inference based on symmetry here that probably works in many cases. It's probably the right thing to do in terms of figuring out which one's object and which one's background. We also talked about grouping and Gestalt principles, which are rules for connecting image regions together. So we were talking about segmentation before, segmentation and figure ground, but figure ground assignment. And in general, there's a larger problem of putting pieces of an image together that belong together. So we talked about the desk, for instance, that continues behind the chair in that image before. And again, it's based on best guess techniques like figure ground assignment. And these some Gestalt principles that have been known for a long time are laws of similarity. So in this case, you're more likely to see this as a row of squares and then a row of circles because the squares are similar to one another. And why is similarity a good thing to use? And it's because objects themselves will often have more similarity within them than between different objects. So if you look at an object and take measurements of different parts of that object, they're more likely to be more similar to one another than if you take measurements from amongst different objects. Another one is proximity. Again, we tend to see these as grouping, not these. So the horizontal versus the vertical. And again, it's because parts of objects tend to be closer together to one another than parts of different objects. Gestalt principle, good continuation. We would tend to see this wire continuing past this way for a smooth curve. And again, it's because it's a reasonable assumption. It seems to be a reasonable assumption that this is a property of objects that they tend to have smooth curves, that this would in fact be a single object rather than some object branching off in various different directions. And we talked about common fate, where portions of an image move together. This also leads to them being grouped together. Another basic problem, now beyond those that we've talked about, is that of depth ordering. So specifically processing depth information. So the image on a retina, as we said, is 2D. It is a two-dimensional image. It's a flat sheet of retina. And so the question is, how do we figure out how far things are away from us? And as we said, many of the previous problems we discussed to some extent fall out of the problem of the fact that we don't have direct depth information. So how do we figure out how far things are away from us? So we mentioned a couple of basic cues to this, just to give a little flavor, and there are many such cues that have been discovered. So occlusion is one. If one object is blocking another, in this case, the blue is blocking the red, It's a fair assumption to assume that that object is actually closer to you than the other object is. We also talked about perspective projection. The fact that an object is that the light from an object has to pass through the small pupil before it gets to the retina leads to this thing called perspective projection. And one property of perspective projection, one effect of this perspective projection, is that as an object gets closer to you, the image on your retina is going to increase in size. And so your visual system can use the increase in size in order to figure out just how far away an object is from you. So, as we can see here, your visual system does actually use this as a depth cue. When train tracks recede in the distance, they look like they're converging. And the reason they look like they're converging is because the image of those as they get farther away from you is smaller on your retina. So further away equals smaller on your retina. In this case, of course, it's an illusion. This is really a flat image, but your brain interprets the fact that these are getting further away, not that they're actually converging, that they're actually joining together, but rather that they're actually further away from you in space. So your brain is using the fact that it knows that when things are further away, they get smaller to make an interpretation here that these are receding from you in depth. Size constancy is the fact that derives from the fact that our brain knows that when something is producing a smaller retinal image size, that could be because it's smaller, or it could be because it's further away in depth. And size constancy occurs by when your brain is able to interpret the fact that something is producing a smaller retinal image as due to it being further away in depth rather than it being actually smaller. So if we show the actual same image of this guy, but over here where this thing appears to be in the same depth, your brain is now going to interpret this as a much smaller man. But it doesn't look like a much smaller man when it's further out here, because your brain says, oh, the reason that's producing a smaller retinal image is because it's farther away. So it could actually be a similarly sized man to this, but just farther away. And so again, this demonstrates that your brain is able to use its knowledge of the fact that the retinal size is smaller as it gets further away in order to interpret this thing as being farther away in depth. We did not discuss binocular disparity, so we will not be covering that for this exam review. And the final topic, and still this is part of Chapter 3 in the textbook, is Perception 2, which deals with recognition and also perception in action. So what do we see in a moment? There was a movie that was shown in class which showed briefly presented objects and pictures of objects they were able to recognize even though they were presented for less than 100 milliseconds. And so this is a very brief presentation, and yet you're able to recognize those objects. So we're really good at recognition. But recognition is actually really hard, so the best state-of-the-art technologies are not able to recognize these kinds of texts. And even though we as humans can recognize them and read them fairly easily. So the best algorithms can't match human performance. Again, like other things, even though recognition seems kind of easy to do, it turns out to be quite hard to automate. What is recognition? So recognition is recognition, and the idea is that we have some stored representation of objects in memory, and then when we see a stimulus, we try to match those to that stored representation. The question is, what is the nature of the representation? And so again, it gets into this question of the underlying representation. The simplest form of a representation of a model for recognition would be a template model. So if you have to learn to recognize a K, then when you see an image of a K, you store an exact replica of that and then match up some new version of the K to that one. And the problem is, although this is very simple, that it's going to break, it's very brittle, it's going to break very easily. So if you just rotate a K and you have to recognize that, which of course we can do, it's going to fail because it's not going to exactly match. So if you're thinking in terms of just storing an exact replica of the original image, the template model, it's going to be very not robust in relation to any changes in the image. And so this is the basic problem of recognition, is that there always are changes. There are lots and lots of changes that happens between when you originally see an image and the next time that you see it. Some obvious types of changes are changes in viewpoint. So as something rotates, oh well, that didn't work, it's going to look very different. So as an object rotates in space, the image that you're going to see is very different. variability among members of a category. So there are lots of different types of Ks, and you can recognize those all as Ks, even though the images they produce are very different. This is true for other kinds of categories, so lots of different kinds of houses. You can recognize them all as houses, but you may never have seen these examples of a house before, so you have variability within the category. And individual objects change, so people age, such as Bill Clinton, people change their shape based on moving their limbs, and people change their faces based on changes in viewpoint, so this is a rotation depth, but also, in this case, changes in facial expression. And yet we're able to recognize those all as the same person. So what is this representation that we have that allows us to match all these individual inputs to the same underlying representation? So feature-based recognition suggests that what we do is use features that remain stable across variations. So these are all faces, they're all different, but there are certain similarities. In this case, there's various features that are common across all these different examples of faces. And so feature-based recognition for something like letter recognition may say, well, what we're going to do is look at features that are common across all these. So all of these Ks have certain kinds of diagonal lines and certain kinds of straight lines. Don't have any horizontals, don't have any of these curves. And we say, oh, there are those features, they're common across all these examples. And so in order to recognize a K, we look for those features that remain stable across different kinds of Ks. One of the most prominent examples of a feature-based theory of recognition is geon theory, which suggested that the way we overcome changes in viewpoint, so things look different depending on the angle at which we're viewing them, is to extract these volumetric geons, volumetric parts, which can be recognized from different angles based on specific properties. And so in order to recognize a phone, we just need to know that it's made up of a number 5 geon, a number 2 geon, and a number 3 geon in various relations to another. What is special about these geons is, again, that they can be recognized from various viewpoints because there's certain properties, certain features which remain stable across changes in viewpoint. So, for instance, this kind of cube is always going to have a straight edge and a straight axis, which is always going to be present regardless of which viewpoint you view it from, and so on and so forth for all these different kinds of geons. View-based models, on the other hand, are different than feature-based models. What they suggest is that, well, it's not based on certain features that are constant across different changes of viewpoint, but instead, in order to recognize objects from different angles, what you do is you actually have to see them from several different angles, and then there's ways to extrapolate to novel angles based on having seen it from a couple of different views. So this is basically something like a template model, but we can think of it as a template plus. It's templates. So you're seeing a couple of different views, and then you see a novel view. You're able to extrapolate from those views to this new view. So which one is right? Do we use geon theory? Do we actually, how do we recognize things from different viewpoints? Do we use those features that remain constant across changes in viewpoint, or do we do it based on having had a couple of views and then extrapolating to a new view? So one important prediction of geon theory is that recognition should be viewpoint independent. As long as you can extract those geons, you should be able to recognize the object equally well and just as fast as if they're regardless of the particular viewpoint at which you see them. So again, remember we talked about different representations leading to different predictions as to what's easier and hard. In this case, geon theory makes the prediction that it's going to be just as easy to recognize an object from one viewpoint as another viewpoint. But empirically, we find this is not the case, and so view-based theories predict that it might be more difficult to recognize an object in this viewpoint than this viewpoint, because what you've stored up is a view such as this one, and in order to recognize this one, you'd have to do something like, say, mental rotation to get to it. And in fact, empirically, what we say is that it takes people less time to recognize this object, an object under this condition, under a canonical viewpoint, a familiar viewpoint, than an unfamiliar viewpoint. So this seems to suggest geon theory might not be the right account of recognition. Besides these feature-based models and view-based models, we also have to recognize the role of top-down information in recognition. So as we said, once you know there's a Dalmatian here, you can recognize it, and that's true in this particular example as well. You might be able to recognize individual letters based on your knowledge of English words. And so it's important to take into consideration the role of context, and this is a form of top-down information in visual recognition. And we saw this example of the many personalities of a blob. So it's the same image in all of these examples, but based on its context, it's going to be recognized as something different. How do we do this? Well, there's some good evidence that people store up information about what kinds of objects tend to be in certain locations. And so in a certain study, people were able to identify what object is likely to be in a certain location, even if they had not ever seen it in that location, based on their general knowledge of the schema and which kinds of objects tend to occur in certain types of situations. Finally, we talked about the visual brain. So the brain is made, what we think of as being visual areas are spread out across a pretty large portion of the brain, at least 30 visual areas, taking up over half of cortex. So that's a good chunk of cortex being devoted or involved in visual processing. And so what are all these different visual areas doing? Well, one thing we know is that there's all these different visual areas are processing information in a somewhat hierarchical fashion. What this means is information starts off fairly simple. So if you look at neurons in the photoreceptors in the retina, they respond to very simple kinds of stimuli. And then if you look at early cortex, so it's a little further along in processing, so that the retina sends its information to cortex. Well, those neurons are going to respond to more complex types of things like oriented edges. And then further along in the visual brain, as the information converges even further into different neurons, you get higher degrees of specificity and higher degrees of complexities, complex shapes. And then eventually you get neurons that respond, as we said, to faces and also to objects. And so what you get is this further refinement and further complexity of processing as you get further along in visual areas. So that's what all these visual areas are doing. They're doing further and further processing of that original information. There's good evidence that these higher level areas are involved in this kind of specialized kind of processing, even from fMRI imaging. So there are these portions of the brain that seem to respond selectively to faces. And so in fMRI experiments, in a facial recognition task, you'll have this region called the FFA, fusiform face area, that seems to respond characteristically, specifically to faces. And additional evidence comes, again, from neuropsychology, from cases of people who have some sort of damage to portions of their brain will sometimes show these specific kinds of agnosias, and these are particular inabilities to recognize certain kinds of objects, such as faces in prosopagnosia or objects in semantic agnosia. And you saw the video of the prosopagnosia, and importantly, these people are certainly able to see, and they're able to process to a high degree most of the visual information, but they show these very kinds of narrow disabilities to recognize certain kinds of objects, and it suggests that this is really a specialized kinds of processing taking place in higher level regions of the brain. However, as we saw, there is some debate exactly what this kind of specialty processing really means. So is there really a face area in the brain? That FFA, it does respond to faces, and it does damage, if it gets damaged, it does affect facial recognition. But there is some suggestion by others that it's not specifically about faces, but rather the kind of processing that is required in order to recognize faces. So faces tend to look similar to one another, and maybe what this portion of the brain does is actually recognize things, is distinguish between things that are visually similar. And what evidence there is for that is a study by Gautier and Tar, in which they trained people to become greeble experts. These were novel objects that were visually similar, and they learned to distinguish between them. And then they put them in an fMRI, and lo and behold, their FFA, that region of the face that's thought to be selective specifically to faces, was now responding. And so some people have suggested this is an expertise area, not a face area. And this is a general controversy whenever we see a certain part of the brain that's lighting up. If we don't know exactly what it's doing, we just know it's responding to certain kinds of tasks, then there can be some debate as to what exactly makes it specialized for that kind of task. Finally, we talked about the dorsal and ventral streams in terms of the structure of the brain. We know anatomically that the visual information that comes into the occipital lobe gets sent dorsally upwards to the parietal and then ventrally downward to the temporal lobe. And the question is, what are these different portions of the brain doing? So there's two theories. One is the what versus where theory by Archuleta and Mishkin. And they showed in monkeys that if one removes the temporal lobe portion, so that would be the ventral stream, then the monkey who has that done will have difficulty distinguishing between two objects. So that's meant to be a what kind of system. If, on the other hand, you damage the parietal lobe, so the dorsal stream, they may be able to distinguish between two similar objects, but they won't be able to do a task which requires saying where an object is relative to another. And so that's the where system, the what versus where system. An alternative explanation into the dorsal and ventral stream is the perception versus action dichotomy. This has been proposed by Goodell and Milner based on some interesting observations of patients that they have. So, for instance, this case is a patient who has damage to a ventral but not dorsal portion of her brain, and she's very poor at doing a perceptual orientation matching task. So this is what you can think of as sort of a basic recognition perception task, saying whether a line has the same orientation as another. But she's quite good at picking up an object and pushing it through a slot. And in order to do that, you have to know the orientation. So when she has to do a perceptually guided, a visually guided action, in this case, that seems to be largely preserved. And so that suggests that perhaps the dorsal and ventral subserve different kinds of processing: recognition, perception on the one hand in the ventral, and then perceptually guided action in the dorsal. And the last thing we discussed was the fact that recognition and the senses in general have long been thought to operate somewhat independently of one another, but it turns out that they interact quite a bit. So when you hear a voice, for instance, it automatically conjures up an image of a face. And it gets even more dramatic when we look at speech recognition. So if we have to recognize what sound a person's making, if there's a visual cue, a video of a person speaking a different sound, that can actually interfere with the sound that you hear. And that's the famous McGurk effect, which occurs when a person is speaking, visually speaking the sound ga, and you hear the recording of the person speaking ba. You end up hearing neither of those, and you end up hearing some, typically, at least most people will end up hearing something that sounds more like da. And so the idea is that the brain actually doesn't just separately process visual and auditory information when it's doing recognition. It actually can combine these sources of information. So the final conclusion is that recognition can depend on complex combinations of information that can be multimodal from different sensory modalities. It can be a combination of top-down versus bottom-up information. There's no single algorithm to recognition.